Okay, we have just really started to explore the subject now of exponential generating functions. In our two previous videos on this subject, we introduced them and then we used them to solve some simple permutation problems. And what we're going to do now is consider some more of the mathematical properties of exponential generating functions, and we use those as tools to solve some of the more complicated permutation problems that we want to deal with. Incidentally, if you just found this on YouTube, if you would go to the website at digital-university.org, all the videos that we have so far concerning counting problems, combinations, permutations, and all the videos that we've done so far on ordinary generating functions, you find them all there at the website in their proper order. Okay, for now what we want to do is remind ourselves this is the basic form of an exponential generating function, where we have a series of numbers, A0, A1, A2, A3, and so forth, and we multiply them by not just x raised to a certain power, but it's also divided by whatever that exponent is also divided by that factorial in each case. And the reason why it's structured like this, as we've seen in the previous two videos, is that this coefficient of x to the k divided by k factorial, whatever that number happens to be, quite often then that coefficient there tells us the number of ways of performing k number of permutations. And the reason why this is called an exponential generating function, from calculus we learned that e to the x is equal to this expression, and e to the minus x is the same thing, except the odd powers of x's have minus signs by them. So this would be the expression for e to the minus x. Now, for a moment, let's say that we had e to the x, and we subtracted e to the minus x. Then we would see that the 1's would cancel. This would have to be 2 times x over 1 factorial. The even numbered exponents, they would cancel. And for the odd number exponents, it would be 2 times that expression. So, if we had e to the x minus e to the minus x, that would be equal to, again, these cancel, these add up to 2, these add up to 2, as it does for all the odd exponent powers. So this would be equal to 2 times x over 1 factorial plus x cubed over 3 factorial, and so forth, like this. It will continue like this. All these exponents and factorials involving odd numbers. Or, dividing both sides of the equation by 2, we would have e to the x minus e to the minus x divided by 2 equals this expression, all of them involving odd numbers, on out to infinity like this. This would be the hyperbolic sign right here. But that's not important. What is important to us is that sometimes when you're considering a permutation problem and you're setting up the generating function, it turns out to have this kind of form right here, where only odd numbers are involved. And then you have to do different mathematical manipulations on this. Well, knowing then this relationship here can be a great service to you, because whatever mathematical manipulations you have to do in this infinite series, it's a lot easier to do that mathematical manipulations on this expression here. So this is why we show this relationship to you now. Because we'll use it in future videos. Or if we had e to the x plus e to the minus x divided by 2. Now what will happen is, if we add these together, and this adds up to 2, these cancel, and now all those with the even numbered powers end up being multiplied by 2. Here we're divided by 2, so this comes out to be equal to 1 plus x squared over 2 factorial, and now we have strictly even powers and even factorials, like this, and so forth. And again, we show this to you now because sometimes when you're setting up a permutation generating function, it involves only even powers of x, like this, and you have to use certain mathematical manipulations on it. It's a lot easier to do the mathematical manipulations on this expression than on this infinite series. So we want to point out to you these two relationships right here. We will use them in future videos. Now, instead of having e to the x, suppose, for example, we had e to the nx. What would that look like? So let's make some room. So e to the nx that turns out to be equal to, the x is just replaced by nx, so that's 1, that stays the same, plus the x is nx, so we have n times x over 1 factorial, plus for this term it would be n squared times x squared over 2 factorial. Try to keep these in focus, plus comparing these two expressions. For x cubed we have n cubed x cubed, so we have n cubed x cubed divided by 3 factorial, so forth, so that for x to the k divided by k factorial, it's multiplied by n to the k. So if we have a generating function that's equivalent to this, e to the nx, and we want to know, well, what is the coefficient of x to the k divided by k factorial? It is just simply n to the k. Now, sometimes we have this kind of a situation, as you see in our future videos, if you have, say, x times e to the nx. What will that be equal to? Well, that's just this expression times x. So if we go ahead then and multiply 2 by x, we have x plus n times x squared divided by 1 factorial plus n squared times x cubed divided by 2 factorial plus n cubed, this will now be x to the 4th divided by 3 factorial and so forth. So if we have x to the k, this is x to the 4th, this is 3 factorial, so this is going to be k minus 1 factorial here, and it's going to be times n This is 1 less than this number, so if that's k, this would be k minus 1. So, if we have a generating function that involves this expression, x times e to the n x, the terms in here generally follow this pattern here. N to the k minus 1 times x to the k divided by k minus 1 factorial. Well, when we're interested in permutation problems, we don't want to know what is the coefficient of x to the k divided by k minus 1 factorial. We want to know what is the coefficient of x to the k divided by k factorial. Well, if I multiply this by k, that is k factorial. So if I multiply the bottom part by k, I have to multiply the top part by k. Like this. So what we end up then is that the coefficient of x to the k divided by k factorial, that is equal to k times n to the k minus 1. So if we have a generating function and maybe part of it involves this term here, and we want to know, well, what is going to be the coefficient of x to the k divided by k factorial? We know what n is, we know what k is, so in this situation, x times e to the nx, the coefficient of x to the k divided by k factorial is just k times n to the k minus 1. So, we know this is part of a problem here. We know what n is, we know what k is, so to find the coefficient of x to the k over k factorial, we can write it down instantly. So I'm showing this relationship to you now because we're going to use it in future videos to make life a lot easier for us. Let's just continue here. Suppose, for example, we had, say, x cubed times e to the nx. And that was part of our generating function. Then what would this be equal to? Well, that would be equal to this one times x squared. So the first term would be x squared times x, or x cubed, plus n, this is now x to the 4th, divided by 1 factorial, plus n squared, this would now be x to the 5th, divided by 2 factorial, and we go on like this. Here we eventually have x to the k. This is 5, this is 2 factorial, so this would be k minus 2 factorial, times n. This is 5, this is 2, so this is going to be n to the k minus 3. So, if we have this as our generating function, or part of our generating function, we know that in the series, the terms are going to have this general form right here. N to the k minus 3 times x to the k divided by k minus 2 factorial. But again, for our problems, we want to know what is going to be the coefficient of x to the k divided by k factorial. So here, we look at this, we have k minus 2 factorial down here. Well, we know that k times k minus 1 times k minus 2 factorial that is k factorial. So if we modify this bottom part by this, that gives us k factorial down here. If we modify the bottom by this, then we have to multiply the top part by this. So what we're going to find out then is that we're going to have this n to the k minus 3 times these two terms times k times k minus 1, and this will now be x to the k divided by k factorial. So if this is part of our generating function, and we want to know, well, what's going to be the coefficient of x to the k divided by k factorial, it will be this expression right here. And hopefully you can see the pattern that's forming, because what we can do is that we can say, in general, if we have this expression, say x to the p times e to the nx, and we want to say, what is the coefficient? What is the coefficient of x to the k divided by k factorial in this expression here? And the answer is, it is k times k minus 1 times k minus 2 on out to k minus this here, p minus 1, times n to the k minus p. So here we have x to the power times e to the nx. We want to know, if we write this expression out as an infinite series, what's going to be the coefficient of x to the k over k factorial? That's sort of part of the infinite series that interests me. And the general formula for it is, the value of p is it's going to be k times k minus 1 times k minus 2, all the way on out. And we can write this last part here as k minus p plus 1 for this last term, times n to the k minus p power. And that will be the coefficient of x to the k over k factorial. And for many more complicated problems there, that coefficient, which is this expression right here, that's what we need to know to solve the problem. So that's all we have to say for this video. We just kind of wanted to introduce to you the kind of thinking that's involved in finding the coefficient of x to the k over k factorial in different circumstances. What we found is that if we have e to the nx and the coefficient of x to the k over k factorial, that's just n to the k. If it's x to the first power times that, then the coefficient of x to the k over k factorial, that is just simply k times n to the k minus 1. Or if we have higher powered x's, x squared, x cubed, all the way up and say xp, then in this case here for x squared, it is k times k minus 1 times n to the k minus 2. That is the coefficient x to the k over k factorial in this expression. Or if we have x cubed times e to the nx, the coefficient of x to the k over k factorial, it's this, k minus 1, k minus 2, n to the k minus 3. Or in general, the expression is this. Here we have x to the p, e to the nx, and it's going to be k times k minus 1 times k minus 2, all the way now to k minus p minus 1 times n to the k minus p. And that'll be the coefficient of x to the k over k factorial. And again, we'll make use of this in future videos, so it seems a bit murky right now. Hopefully we'll clear it up later on when we use this to solve more complicated problems. So come back and join us for those videos, and we'll try and solve some more permutations.